How are you doing here? It's third day. You have one more day, and we can do it, okay? So I'm glad we had a good introduction on Dragonfly because I'm going to talk a little bit more on one of these instruments. So I'm Victoria. I'm working at NASA Goddard Space Flight Center. My background is aerospace engineering, so I'm not a flight software person, but I'm learning a lot, so that's great. So I'm coming from Goddard. I work with a lot of great colleagues here who helped put this talk together, and we had some discussion about autonomy, and we don't have a lot of autonomy on Dragonfly, and especially on the DRAMS mass spectrometer, but a tiny bit. I'm going to talk a little bit about it. So in my department that is named Planetary Environment Laboratory at Goddard, we have built mass spectrometers for a very, very long time. So in case you're not familiar with mass spectrometry, as I was not 5 years ago, and now I'm doing a PhD on it because I guess it's super fascinating, we are using this instrument on board space missions since 1970s. And basically, it gives you the molecular composition of samples. So that's why it's been used on a lot of flight missions in space. So basically, you can put a sample in different types, different formats, solid, liquid, gas, and then you have a whole process that ionizes the sample and then get your data, that is a mass spectrum that you can see at the right of the screen. Or you can see a better example here coming from MoMA. I'll refer to MoMA a lot. So MoMA is Mars Organic Molecule Analyzer. It's a mass spectrometer that will be on ExoMars, and Dragonfly mass spectrometer is heritating, hopefully that's a word. A lot of heritage. I'm French, by the way. A lot of heritage from this ExoMars mission. So in our department at Goddard, the Planetary Environment Laboratory, we've built a lot of mass spectrometers, as I told you, and here are the missions where we contributed to it, and my team, flight software and ground software team, have been building the software and testing the software for these mass spectrometers instrument on board these missions. And we're currently developing other missions in, again, the same lab for Venus with the Da Vinci mass spectrometer, the ExoMars mission that I just referred to, that is a European mission with the NASA instrument on board, and Dragonfly, the most exciting mission ever. So I think we all know that space is hard and we have a lot of challenges. And the mission operations is one of the problem we have. So for Mars and for other planetary targets, it's kind of easy, and we have these operation cycles where we define the experiment, we give the homework, as I said, to the rover, to the instrument. This mission is doing the homework, and then we send back all the data back to Earth, and the scientists, the awesome scientists, look at the data, process the data, and decide what to do next. And we repeat this over and over again. This is great. This is what we've been doing for Mars mission in our lab, in other missions as you've been working on. But if we're targeting further away targets, like very, very further away targets, it starts to be more difficult with communication delays, with latency, with bandwidth problem. And so we want to do to give some autonomy to these missions, and that was a great panel yesterday with Steve and everybody at lunch discussing this. So one part of my projects is, okay, that's working, is how to make these instruments a little bit smarter. So because the mass spectrometers we're developing at Goddard, basically you can see on the x-axis here, 3 types of mass spectrometers that are quadruple, ion trap, and Orbitrap. So quadruple is on Curiosity rover and collected X amount of sample, as you can see here. ExoMars with MoMA is going to collect a tiny bit more, and the instruments we're developing are going to collect way more. But we won't be able to send back all the data back to Earth. So at some point, we need to make this instrument a little bit smarter. So that's what my research focuses on, science autonomy, to give some basic tasks to this instrument. And that's a lot of data science process that we were trying and are trying to have onboard future space missions. But when I started at Goddard, Dragonfly was already selected. Autonomy was not really there yet. So we had one requirement that I will discuss later in my talk, that is autonomy on Dragonfly, but it's not using any ML, it's not using any AI, it's just software. So that's why I'm here. So we had talked a little bit of Dragonfly, so thank you, Gina, for the introduction. Dragonfly is amazing, and I wish my talk was yesterday because it was exactly 370 years ago yesterday that Titan was discovered. So it's 370 years plus 1 day. Titan is great. Titan is a great planetary body. It's a moon of Saturn. There is a lot of cool stuff about it that I try to summarize here. I guess the main thing is that there is a surface pressure of 1.5 bar, and that we know that there is a deep interior ocean of liquid water. So that's one also of the reason we want to go there. And there is kind of a water cycle, but with methane, with nitrogen and methane there. So we know that there is some really cool stuff happening there. So that's why we're sending Dragonfly, hopefully in the 2030s. But also, as you can see here at the bottom of the screen, it's far. It's very far away, 70 to 90 minutes to communicate with Titan, when we can communicate with it, because sometimes we won't be able to. So we need to have some autonomy with autonomous flights and hopefully some autonomy in the mass spectrometry measurements. This is the best picture ever. So that was my background for a very long time. I changed recently, but I think it's just very rewarding to know that we're working on space missions, space exploration, and this is going to be Dragonfly hopping on the surface of Titan in the next decade, hopefully. So on board Dragonfly, we have a lot of different instruments, and two that are worked a lot at Goddard are Draco and DRAMS. So DRAMS is the one developed in my department. It's an ion trap mass spectrometer that will measure the composition, the molecular composition of different samples from the surface. And what is cool with this instrument is that we have two mass spectrometry modes. So this is more chemistry, so maybe less interesting, but the laser desorption mass spectrometry and the gas chromatography mass spectrometry, I'll talk way more on the LDMS part after. I'll refer to LDMS and GCMS because the whole acronym is super long to say. And we just really like this instrument. So what is cool again with this instrument is that the brain of the instrument is a mass spec. So that's giving you the molecular composition. But how the molecules are being ionized are coming from two different ways. We have the laser part, the laser desorption part, and the EI part, the electron ionization part of the GCMS part. So on my talk, I will talk more about the LDMS part. And we're here to talk about software, I guess. So you have all the introduction of the mission and how passionate it's going to be. I'm part of the ground software team. So I work closely with the flight software team developing the flight software for DRAMS, and we're developing the tools to be able to have all these great mass spectrometry experiments on board. So I'm dreaming of this almost every night. No, that's not true. But that's basically what I'm working with when I work with DRAMS. It's the GPS, the gas processing system. So it's how the molecules are going to be moving to get to the ion trap. So I have a laser here. Okay. So here, hopefully you can see online too, I'm not sure. ITMS is the ion trap mass spectrometer. So that's the brain of the instruments. That's where the molecules need to go to be able to have at the end the mass spec data. And I told you, we have two ways to ionize the sample. We have the laser part where the sample is coming from Draco. Here it gets to the ITMS and then basically get measured here, and then we eject everything, we vent everything. The other part is the GCMS, where we have a lot of different options, working with CNES to get different chemistry measurements. But again, I'm going to focus on LDMS. But basically, my job is to operate these valves, these heaters, and work in collaboration with flight software to be able to run any of these experiments. So I really like this slide. I think it's more for me than anybody else in this room. But it's really to have the difference between flight software and ground software. So flight software communicates with the hardware directly, and ground software, when I'm working, is sending the flight software comments to upload the different files, the new flight software image, and we're not using Rust. We are using BASIC scripts. So who is familiar with BASIC? Yes, we have some. So we also, in our team for the ground software, we decode and display all the telemetry of our own tools that we have been developing for X number of mass spectrometers missions. And all of our ground software code is using C++ and BASIC, and it's shared between all our different projects. So this is also the flight software block diagram for DRAMS. As you can see, it's communicating with the lander, so with Dragonfly that Gina just presented about, and talks a lot also with Draco. Draco is the acquisition sample, so it's how we get the sample from Titan. So we communicate to Draco through the lander. We always talk to the lander. We never talk to any other instruments. The brain, the CCDH board controls a lot of other boards. So the yellowish boards, looks yellowish, hopefully. CTL, PT, VH, MMC, LEU are the different subsystem boards that we work with to be able to operate our valves and heaters and laser and pumps to be able to run these experiments. We are not as lucky as APL with hardware. So we'll say that we have simulators for now. So all these different boards are interacting together to be able to run the mass spec instrument. It's a lot of things happening in parallel. So my role in the ground software team is to develop the scripts. So basically the scripts that we write in BASIC and not in Rust or C++ or whatever, provide sequencing and logic to execute the experiments, the LDMS experiment, the GCMS experiment. And what is great with this interaction between flash software and scripts and what has been working with the mass spec onboard Curiosity, with the mass spec onboard ExoMars, is that it's very flexible. So basically I'm sitting with the scientist, the expert in mass spectrometer, and they say, hey, I really want to run this experiment. Can we change and tune these parameters, this oven temperature, this column temperature, to be able to do the science they want to do. So for the scripts, we will be able to update them very regularly during operations, when for the flight software, that won't be the case. So for the ground system context, we have all the scripts on board the CCDH, also talking with the DRAMS flight software that talks to the hardware, the laser board, the GPS board. GPS, again, is the gas processing system that talks with the valve, the heaters, the different columns, temperatures, and make the science happen. So here I will just go through all the animations. But you can see how everything is being interacted together between the DRAM scripts and then the ground data system that we have in the lab at Goddard to be able to post-process the data, to archive the data, and to have our scientists look at the actual science data, not the raw data. So again, I mentioned we are not as lucky as APL, and we don't have all the hardware for now for our DRAMS mass spectrometers. So we are using a lot of simulators that my colleague Mike Burkhardt developed, and that are great. So for the scripts, again, DRAMS is going to Titan. It's pretty far away, so it's very limited data volume, so every bit counts. And what is really cool with these scripts is that we have to make it a little bit more autonomous, and that's what we're working on. So that's really the main difference with all the different scripts we've been writing for Mars, mainly Mars missions. And again, it's coming up soon, this autonomy part. Also, what is really cool is that we can optimize and test these scripts with all the experience we've had on SAM. SAM is the sample analysis at Mars and Curiosity, on MoMA, on ExoMars. So it's been proven, this script verification has been working and on Mars for 12 years with SAM, and has been experimented on MoMA for several years too. Also, what is going to be different for us for this time is that we call it a flight first model. So that means we don't have an engineering model first. So all the scripts and flight software will be tested on the flight model first. That's kind of scary. So we cannot really mess up, but it's a budget question here. So flight software is going to interpret the different text files that basically are the commands to run the experiment on Titan. Again, I mentioned it's based on BASIC. That is it's a great programming language. And it's highly flexible. And so we have all this interaction with just an example of a script, basic one. But basically, one LDMS experiment is very flexible because we can have several scripts based on the laser energy we want to use, the laser pulses. So it really gives a lot of flexibility for the science to happen on Titan. Here you can see the ground software main tasks to communicate with the mass spec, to visualize the data in real time. So we have all these tools to be able to visualize in real time. By real time, I mean, there is bandwidth, right? We are going to Titan. But when we're in the lab, we can see all the data in real time, process the data, and then archive everything on PDS, Planetary Data System. Okay, I told you I was going to talk to you about LDMS. So this is just a gas flow diagram, again, when we are running an LDMS experiment. So I try to blur what is not very useful for LDMS, and I still have my laser. So the sample is coming from here. We have a UV laser that ionizes the sample, and then the magic happens here, and then we vent the sample. LDMS again, so I'll again go through all the animations here. We create the ions with the laser. We trap the ions in the brain of the instrument. We are able, that's again very magic, to manipulate these ions. So what that means is that we can say, oh, we really want the green ions because they are going to tell us more about prebiotic chemistry. So we can target these ions and isolate them and then do more experiments on these specific ions. To me, it was crazy when I heard about that. I'm an aerospace engineer, I was not a chemist, and I was like, wow, you can do all this stuff in the stuff that looks like a microwave. That's really, really impressive. So we can do ion trapping, ion isolation, ion fragmentation. I will talk more about it, and it's all about RF frequency. But really, I know we are very interested on the autonomy. So we have this type of experiment that are named MSMS. So, or tandem mass spectrometry, and basically we can play with this RF frequency, the radio frequency voltage, to be able to isolate the ions and do more magic. So MSMS is a technique to use to analyze specific ions where we isolate them and we are able to fragment them more. So it's words, I like diagrams more. So that's a mass spec. On top of your screen is the first experiment, the first full mass scan. And then we say, oh, this peak at 260 is super, super interesting. Let's see if we can isolate this specific peak here and isolate this specific one here and fragment it more. And that's where the puzzle pieces are basically like, this peak is being broken down in several other peaks, and scientists who have a brilliant chemistry background are able to understand more the molecules and then the potential prebiotic chemistry on other planets. So on Mars, we can do this MSMS experiment, but basically what happens is that we send back all the data to Earth, and then the scientists at Goddard will say, oh, we really want to do MSMS on this peak. It's 20-minute bandwidth, 20-minute bandwidth the other way, so we're able to wait a tiny bit for the experiment to be performed and send the other homework and say, okay, do MSMS on this peak. On Titan, we cannot do that, and it is one requirement to have this MSMS automation on board Dragonfly mass spectrometer to be able to have this whole process of selecting the peak and then fragmenting it more to get the whole process autonomously. And it's not working anymore. Here we go. So it was a lot of discussion with scientists. Yesterday, it was a great question about how do you work with scientists during the panel. How do you work with scientists to tell them, hey, this is what I need, this is, because they want everything. If you work with scientists, you know they want everything all the time. And I love my scientists. But here, they understand that there is no choice. At some point, we need to just understand how their brain works, and we cannot do MSMS experiments on the whole 10 picks. So it was a lot of back and forth. Again, you'll have access to the slides. But how do you decide when you have a PhD in chemistry, how do you decide which peak do you do MSMS on, and then what the whole process? So that's where we had a step-by-step process where basically we'll have the list of the most intense peaks that will be like set up, defined by the flight software that will run a script picking algorithm. And then we'll have an exclusion list. This exclusion list will be, okay, thank you. The exclusion list will be, we already perform MSMS on these peaks, so let's not waste time and redo the same experiments. Let's learn new stuff. And then it will be a yes/no question, do we do MSMS? And then we perform this MSMS experiment and update the script. So that seems pretty straightforward. But then when you ask the scientist, how do you define which peak you do your MSMS on? And then you need a PhD in chemistry. So that's the whole high-level picture of how they think about it. Again, I will not spend time reading it. You have access to the slides, but I just want to say this is just incredible to be able to collaborate with the experts in this field, both in the flight software that have been developing flight software for mass spectrometers for years, and then experts like Desmond, Mike, and Mike on this work. Okay, I want to have time for some questions, so this is my last slide. I know it's strange times. I'm coming from France, so I can see that everything happening right now, we'll say it this way. But we're doing very challenging things, especially right now, with people not able to go to conferences or whatever. But I think it's important to know that we're doing also amazing things. So here is kind of a pep talk, but we're not only like working on cool stuff, going to Titan, you know? We're like also inspiring other people and future generations. But okay, lessons learned. I think really the main thing is the collaboration between software, the flight software team, and the scientists. The scientists are kind of my client, I guess. But it's really being able to just knock at their door and say, hey, what do you need? How does your brain work? It's kind of a weird question, but it's really, really essential for us to be able to do our work and in the future, also inspire a new generation. So we have a lot to do this year for drums. We are developing these scripts, testing these scripts on simulators and hopefully hardware at some point. And then we had a lot of discussion for this autonomy one day to be on future missions. And I think we had a lot of discussion of developing and space-proofing better onboard computer to be able to do AI. I do a lot of AI on the side to be able to have more autonomy on board these missions. And thank you. I will take any questions.
Let's thank Victoria.
You
All right.
got a
Any
friend
questions
in
from in the
me.
house?
You
Side there?
got one back here.
If you had the time and maybe a little bit more budget, you get a slightly different computer, what autonomy would you want to add to the Dragonfly mission that you've been working on?
Thank you. It's a great question. So I'm sure there is some more autonomy on the Dragonfly level question. I'm more specialized in the mass spec part. I think my dream, and I hope to see it in my career, is to have the actual interactions between instruments. Meaning, like, if you think of Curiosity, we have, again, a mass spec. Sorry, I'm fascinated by mass spec now. But we have other type of XRD instruments. And you can see the teams on Earth, the Kemen team, get their data, they work together, then the SAM, sample analysis, and Mars get their data, work together. And the interaction exists, but on Earth, and it's like, oh, I saw this in my data, I saw this in my data. What if we could have that on board? Like my instrument, my first instrument sees this, my second instrument sees this. How do we collaborate to make the next measurements even better? Like how do we tune these next measurements so that the laser energy gives us these type of molecules, whatever, So really the synergy on board the spacecraft will be the dream.
All right, we're going to take an online question from Peter Feidelman. How do you decide what science autonomy to put on the main flight computer versus on the instrument?
I'm sorry.
How do you decide what autonomy to put on the main computer or the instrument?
If it was me deciding this, I would decide autonomy on board each instrument and then on the whole mission too. But I'm not in charge, and I think it's better here. So first, there is a budget question for sure. And then second, there is a trust question. What has been very fascinating here, coming from a more engineering background, is the scientists really, really, really want all their data. And that makes sense. We were sending multi-millions dollar mission. So we want to make sure we send back what is interesting. So it's again, a battle between risk and money and trust to make sure we are doing the science goals we want to achieve and getting the scientists what they want, but also giving management and budget people what they want.
Okay, we probably have time for one very quick question, if there's one more. No? All right. Well, Victoria, thank you very much for your talk.